adiabatic changes. So let's now examine the adiabatic expansion of an ideal gas. As the gas expands, work is done. That is, the value of W is negative, less than 0. Because the process is adiabatic, we know that there is no heat transfer, and thus the value of Q must be equal to 0. And that means, because delta U is equal to Q plus W, that means that delta U must be less than 0. That is, the internal energy of our system has to go down as our gas expands. So the change in internal energy of an ideal gas when the temperature is changed from some initial temperature Ti to some final temperature Tf, and the volume is changed from an initial volume Bi to a final volume Bf, can be expressed as the sum of the internal energy changes of 2 steps. In the first step, only the volume changes and the temperature is held constant at its initial value. So we're initially at some value Ti, and all we're doing is changing the volume, which we have on the bottom axis here. We're changing the volume along this step there. So now we're still at Ti, and now we're at Vf, our final volume. Now, the internal energy of an ideal gas is independent of the volume occupied, and that means that the internal energy change for that step is 0. That is, the internal energy is constant for that step. In the second step, then, the volume is held constant while the temperature is changed. So we go down that step there. And for this step, then, we know this is true. So the internal energy change, delta U, is equal to the constant volume heat capacity, Cv, times the temperature change, so Tf minus Ti. That is, the internal energy change is equal to Cv delta T. Now, because the expansion is adiabatic, the value of Q, the heat transfer, is 0. And remember that we know that delta U is equal to Q plus W. Well, if Q is 0, then we know that the internal energy change, delta U, is equal to the work done. And in this case, we're fixing the work as adiabatic work. So the WAD there is the adiabatic work done. And this means that now the adiabatic work done is equal to the constant volume heat capacity, Cv, times the temperature change. So we can show that for a reversible adiabatic expansion of an ideal gas, the final temperature is equal to the initial temperature times the quantity Bi over Vf to the power of 1 over C, where C, as the value given here, the molar constant volume heat capacity divided by R, the gas constant. And if we then raise each side of our equation to the power of C, then we get Vi times Ti to the C is equal to Vf times Tf to the C. Now, we can also write a similar formula for the pressure. This is for the reversible adiabatic expansion of an ideal gas. We've got Pi times Vi to the power of gamma is equal to Pf times Vf to the power of gamma, where gamma in this case is now the molar constant pressure heat capacity divided by the molar constant volume heat capacity. And for a monatomic ideal gas, the molar constant pressure heat capacity is 5/2 R, and that means that gamma is 5/3. For a nonlinear polyatomic ideal gas, then the molar constant volume heat capacity is equal to 3R, and that makes gamma 4/3. Now, curves of pressure versus volume for an adiabatic change are called adiabats. And a reversible adiabat is shown over here. Note that because gamma is greater than 1, the adiabat falls more steeply than the corresponding isotherm does. So if we're looking at the red curve here, that is the isotherm, where we're showing that pressure is proportional to the inverse of volume. The blue curve here is the adiabat, so we're not allowing heat to flow. That is, the temperature is changing. So here, pressure is proportional to 1 over volume to the power of gamma. And again, because gamma is greater than 1, then if we plot pressure versus volume, where now we're ignoring the temperature change here, then the blue curve is going to drop more rapidly than the red curve is. Now this makes sense because we know that the pressure is going to drop as we lower the temperature. So if we're lowering the temperature and we're increasing the volume, then the pressure should drop faster than if we're not lowering the temperature. So that was adiabatic changes.